Welcome to the 2017 Geodesy Bowie Lecture. I'd like to start today's event with the awarding of the Geodesy Section Ivan Mueller Award. This is an award that is presented by the Geodesy Section in recognizing major achievements in service and for leadership within the field of geodesy. The award this year is going to Ken Hudnut. I'm going to ask Gerald Bawden to come up at this time and give the citation.
Thank you, Susan. I'm going to read a quote from Scott Pace, who's the Executive Secretary of the National Space Council. Ken has been a leading model of scientific leadership and public service for almost 3 decades. He is pioneering of high precision GPS techniques, has contributed to the understanding of seismic fault structure and behavior. He played an important leadership role in the design of the GPS L1C signal, which will improve the worldwide service provided to GPS for billions of users. Finally, his work with the USGS continues to contribute to the management and reduction of risk arising from earthquakes and other natural hazards that benefit the public. I can say that Ken has dedicated much of his research career to serving the geodetic community. He's often working at the highest levels and behind the scenes to ensure that the research community and society will benefit from geodesy. Through Ken's vision and leadership, we learned that it was possible to understand tectonic processes by installing continuous GPS array, named SIGN. He also used basically airborne LiDAR to characterize tectonic deformation before and after an earthquake. Ken has become the bridge between the earth science and the emergency response community, communicating hard science to decision makers and educating the public with the shakeout. The shakeout drills in 2016 involved 28 regions. More than 55 million people participated worldwide. But Ken's most significant contribution to geodesy and actually to society, it will be realized when we first launched the Block 3 GPS satellites. Ken co-led the design of the GPS L1C signal. This signal will be stronger and more ionospheric resistant and will improve accuracy in challenging environments and will enable low power phase positioning of small devices. That means you'll be able to get phase-based GPS with your iPhone, smartphone, Androids. When L1C begins broadcasting, the global community, including 6.1 billion smartphone users, will appreciate the improved GPS experience, but few will realize that Geodesy Section's own Ken Hudnut is the one to thank.
Ken, please come up.
So I'd like to start out by thanking Dana Coyle and our children, Alexa, Olivia, and Brock, and my whole family, especially my grandmother, Olive Smith, who was a PhD biochemist and shared with me her love for science, and I think I owe a lot to her for that. Their collective inspiration and support was important to me, and also my employer, USGS, for the freedom to pursue collaborative projects. All of these examples that you've heard are team efforts, so to be singled out is really nice of all of you, but also it doesn't quite feel right to me, I must admit. But I do want to thank the AGU Geodesy Section, especially Susan Owen, President, and President-elect Megan Mueller and the committee, and also Gerald and others who supported this nomination, for the honor of being selected for the Ivan Mueller Award. I never expected such a recognition, and I'm humbled, especially by Scott Pace's kind words in the citation that's also published in EOS. And because many of you may have read that quote and heard Gerald's citation, I feel from here out I should kind of go off script a bit. So I'd like to use the rest of this time to complement those words a bit. So I wanted to say that I'm excited about the future. which may seem a little bit crazy in this day with all that's going on, and we listen to each tweet. But anyway, here's why I'm excited. As we keep learning more with each big earthquake or other natural disaster event, technology applied to our science is allowing us to leap ahead each time. As the new AGU video says, what will you discover? It seems to me that each of you, all of us, can realistically now hope to discover quite a lot. Many world leaders now demand the knowledge that we can uniquely provide as they make decisions that will help us all to face existential threats to humanity. For these reasons, I believe we all deserve to share hope and excitement about AGU's message of discovery. Let's keep working together to fuel discoveries and do our part to benefit humanity. This award promotes teamwork that in turn fuels the innovative thinking needed to answer big scientific questions that remain. Let's keep collectively putting new and improved GPS, GNSS, and imagery and our collective mental abilities to full effect towards benefiting humanity and towards discovery. You can do it. Thank you.
Thank you, Ken. So it is my great honor to now introduce our 2017 lecturer, Bowie Lecturer, Dr. Tonie Van Dam. Dr. Tonie Van Dam has been a professor at the University of Luxembourg since 2008. In 2017, this year, she was appointed Vice President of the University of Luxembourg for doctoral education and training, gender, and international relations. Going back a bit further, Tonie received her PhD in geophysics from the University of Colorado at Boulder in 1991. She is probably best known for her work in elastic surface mass loading and its observations by a variety of geodetic techniques. She also has a number of research projects using comparisons between GPS and absolute gravity to understand glacial isostatic adjustment and other processes such as caldera inflation and deflation. She's also been busy investigating ideas for new satellite gravity missions. While doing all that, she has served as president of the Geodesy section of the European Geophysical Society and twice been elected secretary of the Geodesy section at AGU. In November 2017, she was elected to the Luxembourg Academy of Sciences. This afternoon, she will give the AGU Bowie Lecture entitled Using GPS and Absolute Gravity Observations to Separate the Effects of Present-Day and Pleistocene Ice Mass Changes in Southeast Greenland. So I'd like to welcome Tonie up. Before she gives her lecture, she gets to receive a plaque, which we will then take back from her so she can give her talk.
Thank you very much. Thank you. Thank you very much. Thank you. So, how do I point? Do I point with this?
You can click that, or you can use those two.
Oh, all right. I already went the wrong way. Oh. All right. So, I'm humbled and honored to have been to receive this medal and to follow in the path of so many excellent geodesists before me. Tonight I get to talk to you about a project that's gone on for a very, very long time. Many of you have probably heard parts of it, but tonight I get to tell you the final story. We finally were able to have enough observations to put a nice story together for what we've done in Greenland over the last 20 years. So, without much more waiting, let's get going on this. Tonight I'm going to talk about these observations in Southeast Greenland, absolute gravity and continuous GPS. The motivation for why we do it, you all probably know why we do it, but I'm just going to remind you, since this is a public lecture, what do we know about present-day ice mass changes in Greenland, and why do we know what we know? Then we get to my experiment. What can GPS and absolute gravity observations contribute to learning more about glacial isostatic adjustment? And then finally, what's happening in the southeast of Greenland? Now, the southeast of Greenland is really an interesting place to work because unlike the Great Lakes or other places in Greenland where you have a lot of geologic evidence to be able to work backwards and figure out what the ice mass model was, this data is non-existent in southeast Greenland. So our work there is kind of important. Did it again. All right, why do we need to worry about the ice in Greenland? Well, you all have seen this temperature curve of the global temperature, and it's derived, it's a very, very robust curve. It's derived from data over the oceans, it's derived from data over land, it's been corrected for heat islands, all sorts of things. And what it demonstrates is that since the late 1800s, the temperature, global temperature has risen by almost a degree centigrade. And most of this rise is attributed, of course, to the increase in the amount of greenhouse gases. Sea level rise, what causes it? Why do we lose ice? Global warming increases the volume of water in the ocean basins, and it happens for two reasons. Temperature goes up, the volume of the oceans go up, but the volume increases because of the thermal expansion of the water itself due to the temperature rise, but also because we've lost ice from the ice sheets and glaciers. The largest contribution, according to models, the latest models of the IPCC, indicate that we need to worry mostly about thermal expansion, the continental glaciers, but also Greenland. Greenland even more than Antarctica. What we have here in this figure is, I don't know how to do this, get the... All right. I'm pathetic. All right, back. All right. So where do I do this? Over here or over here?
Yeah. Maybe you need.
It's not working. Okay. All right. Okay. All right. I cut out a lot of slides, so I've got plenty of time. You'll know the end of this before I even get to it. All right, so the big gray squares on this figure are the averages of different forward models of the sea level rise. And the colored crosses below each of those models tells us the relative contributions of things like the thermal expansion of the oceans, glaciers, and Greenland, which is what I'm talking about today. So let's just talk about those three. And if you look down there, you see that Greenland is a pretty big contributor to all of these observations. Thermal expansion is the biggest. And so this is why, this sort of explains why we need to worry about Greenland when we're talking about what's going to happen in terms of sea level. Okay, let's make this talk relevant for where we are. What happens when sea level rises? Well, we've seen a lot of stuff happening recently. First, you have the inundation of significant coastal areas. You have an increased threat of flooding and coastal destruction from storms, which is related to the mass of water that goes from the oceans to the atmosphere. And this picture here shows the areas that will be inundated by the ocean if Greenland melts entirely. So that's a sea level rise, a predicted sea level rise of about 6 kilometers, yeah. We can't change what will happen, but we can prepare. So we can't change what's going to happen with sea level rise. I think it's a little bit too far gone, but we can prepare. We can prepare these areas by trying to understand our models and coming up with very, very precise models for what's going to happen. So we need to estimate the mass loss, because the mass loss of Greenland is the parameter that will actually give us sea level rise. Let's see if I'm going the right way. So what do we know about Greenland already? Well, we've had airborne laser altimetry since the mid-1990s, and that's told us a lot about the thickness of glaciers and how they're changing, the front of the glaciers is moving back really quickly with time. We've had satellite altimetry from IceSat and Cryosat, which is also telling us about what the surface of the ice is doing itself. Satellite imagery has also been providing a lot of information on the velocity of glaciers and the calving fronts, how they're moving back really, really quickly. It's pretty clear from all of these techniques that Greenland is losing mass, but by how much? These remote sensing techniques, they give us volume change, or they give us a change in surface. They don't tell us what the mass is, and it's important. The mass is what we really need to understand to get an estimate of what the sea level rise itself will be. And mass is volume times density. We all know that. So we need to assume something about the density of the ice. New snow deposited on the top of the ice has a density of about 50 to 70 kilograms per meter cube at about 800, and it has a density of about 830 kilograms per meter cubed at about 80 meters depth, and down past about 100 meters, then it reaches the ultimate density of about 917 kilograms per meter squared. At this point, it's under so much pressure that all of the air bubbles have been compressed out. So if we have to convert all of those volume changes and those surface changes into a mass, then which volume are we, which density are we supposed to use to make this conversion? Now, GRACE came along in 2002, and for me, in my experiment here, it was pretty depressing. I thought, what am I doing this experiment for when GRACE seems to be able to do everything except make a martini in the afternoon? So this is a picture of GRACE, and it shows the mass loss on the ice sheet since about April 2002. If you just Google GRACE Greenland, you can see this figure by lots of scientists these days. But there are still some minor problems with GRACE. The size of the footprint means that if you're looking at places where the glaciers and the ice sheets are emptying out into the ocean, you're measuring the ocean gravity change as well as the change on the ice sheet itself. We do have uncertainties in the background models, particularly in GIA. And remember that what GRACE is measuring, it's measuring changes in gravity that need to be converted to mass change. And gravity changes for a lot of other reasons than just mass change, in particular glacial isostatic adjustment. And depending on which model you use and which GIA model you use as well, 30% of the signal that we're seeing in GRACE, depends on the area, could be coming from errors in the GIA model itself. So the question then is, well, GRACE is so good, it's so consistent, can't we just model GIA? Well, this is a picture of an ice model, of GIA over Greenland, where the ice model is Ice 5G, and the Earth model is PREM, and viscosity model 2. And you see that it's pretty variable. You can have the crust uplifting, you can have it subsiding, and so to forward model GIA, you need a really precise ice history model, but you also need to understand the viscosity of the Earth, and that is still being debated today. In addition, there are some places on the Earth where there's just no geological evidence at all to help us figure out what the GIA signal should be in certain regions. Well, what about this idea of using geodetic techniques to figure out present-day mass change? We do it all the time. We correct geodetic measurements for atmospheric pressure change, for continental water storage, for snow. So we could use elastic loading theory to try and look at what's happening in Greenland today. The surface displacement of any GPS station is proportional to the surface mass load, and you just need to know what area of the load is changing. And these observations here will give us the mass directly, whereas the other ones we need to do the conversion. So this looks like a pretty good idea. But GPS is also sensitive to GIA. If we put GPS receivers on the bedrock around the Greenland ice sheet and measure the 3D displacement, we should be able to invert for present-day mass change, but the GIA signal is in that data as well. So the question then becomes, I just said all of this, so skipping. We need to separate the signals. And how do we separate the signals? Well, there's no way that you can do it with GPS alone. In fact, John Waugh wrote a paper with his postdocs at the time in 1995, and he theorized that if we measure uplift and we also measure precise absolute gravity change, then we can solve for the GIA signal itself. Now, it's true that in this situation, we're going to have a very local or a very regional solution to what's going on, and that will never compare with what we can do with GRACE. But it can provide information where no other observations or other techniques can provide, tell us what the GIA signal is there. And even if it can't tell us everything that GRACE can tell us, we can get a pretty good grip on what the GIA signal is, and then we can use that observation to go back and fix the GIA models in the GRACE data. So it does contribute. I had originally a few pages of math in here, and then my dear friend said, oh, you have to cut those out. So we're going to skip the math, and if you're interested, the paper on this was just published in Earth and Planetary Science Letters. For now, I beg you to just trust me, and that we can solve this problem using GPS and absolute gravity. But if you want to read the paper, it's out there. So now we get to the experiment. In the 1990s, NASA, and I was working at NOAA at the time, supported our field work in Greenland. In 1995, we installed our first continuous GPS station out there. It was the second station after Thule had been installed. And we installed it at the GPS station that's now known as Kelly, but it's at the end of the Sandström Fjord, and it's on the southwest side of the Greenland ice sheet. In 1996, we went back and we installed another GPS station in Kulusuk on the southeast side of the ice sheet. And both times we did absolute gravity measurements for the first time. Now, at some point in here, we started to worry about how long this experiment was going to take, given the observational errors and how long it would take us to determine these reliable trends. And that's what the math shows us, is that you really need these reliable trends with really low errors on it, high precision. We found out that with daily GPS observations, we can probably get a reliable trend in 3.5 to 4.5 years. But with the absolute gravity observations, even if we went every year, it would take a decade to achieve a precision of 1 microgal per year on the time series that we were trying to measure. So we knew pretty early on that we were invested in the long run into this experiment. And for that, I have to thank all of the funding agencies for just putting up with it. So when we go to Greenland, we measured the changes in gravity with the FG5 absolute gravimeter. This is the instrument here, and that's sitting on the site that we have at Kulusuk. The measurements are referenced to standards of length and time. The laser is a stabilized iodine laser that gives us length, and then we use a rubidium clock that gives us time. We have a precision of 1 microgal with this instrument, or 1 part in 10 to the 9th. And the instrument can detect a free air gravity correction of 3 millimeters. So it took me a little while to find this. I was trying to find any international coin that was 3 millimeters thick, and it turns out it's a British pound. A British pound is 3 millimeters thick. So if you put a pound under each of those legs, that instrument will measure it. Gravity observations. How many times have we been told, do not put up a table with tons of numbers in it? This is not for you to read all of these numbers. It's just to show you that since 1995, we've taken a lot of observations of gravity in Greenland. We started in Kellyville on the west coast, then we went to Kulusuk, and we're still going to Kellyville and to Kulusuk. But then we added another station, Nuuk, in about 2005, Qaqortoq in 2006, and Ilulissat, which is an important station because it's the outlet of the Jakobshavn glacier. So that's a pretty important site. And that's that big red dot that's about halfway up the Greenland ice sheet on the west side. So I don't have time to tell you the story of gravity all over Greenland, so we're going to focus on Kulusuk. And the reason we're doing that is just to demonstrate that this is a place where there's no geologic evidence, so this is why this technique is really, really important. So here's a picture of our observations. The black line is the daily GPS observations. The red dots are absolute gravity that have been converted into a displacement. And the reason is you need to see both of these on the same map. And this figure shows you some of the problems that we encountered right away. First of all, there's a change in the acceleration. That 10-year time span of observations just went out the window completely when the melting on the Greenland ice sheet accelerated in about 2003. You see the divergence between the red dots and the black line, and that's because of the GIA signal. So since 2003 to today, we're able to see that GIA signal, and I'll show you a little bit more about it. Now, another thing that's really important about this plot are the two data points in 1996 and 1997. Why are they outliers? Well, they're outliers because in 1996 and 97, this hotel was not there. Now, if you look to the right-hand side of the hotel, you can see our GPS on a big cylinder, a pillar there, and that's where we also take our observations. So the hotel was built a little bit lower than the GPS station, and of course it changed the gravity, the DC component of gravity at that station. So those two data points just went in the trash. Now, so the observations that we got, they're just not as easy to deal with as we had hoped they would be. So what we had to do is we had to break the GPS data set and the gravity data set up into two chunks of data. The time series before 2003 and the time series after 2003, because we have completely different linear trends for those data chunks. So this is the result. So after all of the math, after all of the observations, this is what we get. We have results from 1998 to 2003 for absolute gravity trend, 2003 to 2012, and those are in there because they're the dates of the paper. But we have the last observations at Kulusuk were in 2015. And so I have three trends that are here. And if you look over in the third column, you see that what we get is our GIA signal. And all of those observations of glacial predictions for glacial isostatic adjustment, they agree to within the error bars. Now, the thing that's really, really important here also is that the GIA signal is positive. It doesn't sound like a big deal. I mean, if you have GIA, especially in Greenland, if the ice melts, the land should be going up. But if you look at all of the predictions for this part of the world say that the GIA signal should be negative. So ICE 5G, viscosity model 2, minus 1.7 millimeters per year. The same ice history, viscosity model 4, minus 1.5 millimeters per year. You get the idea. So our result, completely different than anything else. Now, could all of these smart people really be doing something wrong? What is going on at Kellyville that really says that the GIA signal is positive? This is a picture of the trace of the Icelandic hotspot. And if you look at the lowest line over Greenland and you see the 40 million year sign, that's exactly where our station Kulusuk is. So we have the hotspot and the North American plate moved over the hotspot, and so it's very likely that the mantle under Greenland is still really hot and very, very soft, making it more susceptible to uplift in that region. So, getting to the summary now. Global warming is causing sea level to rise. Greenland melting is one of the biggest contributions to sea level rise. Understanding ice mass change in Greenland will certainly help us to prepare for the future of places where we have a lot of dense populations that are susceptible to sea level rise. And the geodetic approach is a direct observation of the mass, which is something that doesn't have as many errors as it is converting a volume into mass does. The GPS and gravity at Kulusuk showed here that are used to determine the GIA signal. And it's a very, very robust technique. We bent over backwards in that paper to look at everything that could be causing something wrong. And I'm 100% confident that this is the right answer. The determinant of the GIA signal there is positive, and this accounts for actually 50% of the uplift signal here. Theory predicts negative GIA in this region. So a new determination of GIA in the region will contribute to helping refine the ice history in this part of Greenland. Again, there's no other evidence to do this, so this is an important data point. Our single GIA trend at Kulisuk doesn't allow us to estimate what's happening over a very big region, like GRACE can. But this GIA trend does allow us to make better corrections for GRACE now. And it helps us test future models for GIA. So our estimate of the elastic surface displacement at Kulu, and I didn't point this out, but now this is an improvement over previous estimates because we have been able to separate these two signals out. And now we can use this uplift to also test other present-day melting models. So that's pretty much all of the science I wanted to talk to you about. Now I want to thank the institutions that supported this experiment over the last 20 years, NASA and NOAA, CERES, and therefore the NSF, the Danish Technological University, which has gone through 2 name changes since this project started, UNAVCO, the ECGS, they funded me when I was in Luxembourg, and of course the University of Luxembourg. And then I want to end by saying, what do I want to say? Oh, I want to thank all my friends and my colleagues for supporting me through all of this work. And to tell you, oh God, that I've been able to see a little bit further, but only because I've worked with you all and I've been able to stand on your shoulders. So, thanks a lot. I knew I wouldn't be able to say that. Any questions? Yes, Tom.
If there's hotspot remnants on there, is the viscosity model also problematic? That can be corrected.
Can you repeat the question, Tom?
Since you're under a hotspot,
Yes.
the viscosity is going to be very low.
Right.
And all these GIA models, the viscosity is as critical as the ice history. So
Right.
it's not just ice history, I think it needs fixing in this region.
Yeah. In fact, I would like to throw this out to somebody who probably knows a lot more about these GIA models, because I don't know how well this anomaly in the viscosity may be taken into consideration in these viscoelastic models. Never mind.
Oh, there's a microphone over here. Can you, thank you.
So, thank you. What I was saying was that with the GIA models, we see now last few years more and more that the changes in lateral viscosity are actually pretty important for both the horizontal and vertical changes of the GPS trackers. So there's also a change now to move from these single background viscosity models, which I think you showed a few of them, to models that can incorporate these 3D viscosities, say for example hotspots and everything. And I think what this talk shows pretty well is the importance of those models. So I have a question for that. Will you be doing more of these tests?
Yes, at the other stations that we have around Greenland, we'll be doing it. And we've started to do some observations in Antarctica, but I don't think we're at the Belgian station in Antarctica, and we have two stations there. But it's a really big investment. So people have to, as a community, we have to decide that improving these models at this scale is really, really important, and get Europe more involved in this as well, not just using the US gravimeter.
Okay. Thank you.
Anybody else? Boy, I have fooled you all.
Jeff's got one.
Not all of us, Tony. But no, so with the GIA of several millimeters per year, 5 I think it was, rate uplift, in the early part of the time series, I think Kulusuk was still uplifting a little bit, but for example, Kellyville was subsiding. And so did you actually have a point where there was actually mass gain in the present day within the record at Kulusuk? I don't remember your numbers for the...
No, it's all, let me see. Sorry. No, it's always losing.
Okay,
It's always been losing. And then we're not very far from the Helleheim Glacier as well, and that's just screaming in terms of mass loss.
Right, and so then if Southeast Greenland had a positive GIA trend instead of a slightly negative GIA trend, in terms of the correction to grace and so on, that would be reducing the rate of mass loss? Is that the right sign
Yes.
that we would infer from the present day measurements?
Exactly.
Okay, and then the final one is, do you have any hints? I mean, Kellyville, you've got the long series of data. You haven't published it yet, but any hints about what we're going to see there? Are we looking at many places where perhaps the GIA models are actually quite off?
Well, I don't know about the GIA model in Kellyville. I don't know if there is geologic evidence there, and maybe there's someone here from the Danish university that can answer the question. But yeah, that's the next station we're going to look at very, very carefully. It took forever to get this time series and to understand it really well, and I think it's going to be equally challenging to do the same at Kellyville. I think there was a really big mass change there. Okay.
Any last questions?
All right. Thank you all very much.
So I'd like to thank everybody for coming to the Bowie Lecture. I'd also like to remind people that the Geodesy section reception is tonight. It starts at 6:30. It's over in the Hilton. I forget the exact room. I think it's Churchill something. It is a ticketed event this year. If you don't have a ticket yet, I did check with AGU. It is still possible to get a ticket to go. We've pretty much sold all the tickets, but they said they don't mind selling a few more. So it should be a fun event. So looking forward to seeing you all there.